So sometimes the integral you want to evaluate, f of x, if we look at f of z has infinitely many poles as you head up the above or below the real axis. So according to the residue theorem, you're only allowed to use the residue theorem if you've got a finite number of poles inside the contour. So we can't use the standard semicircular contour in cases where you've got sort of a line of singularities going up the imaginary axis, for example. So the solution is to instead use a rectangular contour, looking like this. The question then is that, okay, the integral you want is along here, along the real axis. As r goes to infinity, hopefully these bits here will tend to 0. But the important remaining question is what happens along here. You need to be able to know what this integral is. So what you have to do, and this is how you choose the size of the rectangle. So if we call this a rectangle of width w, so this point here is IW. Then what you need is that if this is the integral you want, you need to choose w in some way so that the integral from infinity, minus infinity to infinity of x plus IW, so when you're integrating along here, is itself some multiple of the integral you want to find. But importantly, that multiple lambda must not be 1. Otherwise, you'll end up, as you integrate along here, you'll just exactly cancel the integral along here. So whatever you do, you shouldn't choose w to be the period of this function, because then you will just get exactly the same thing, and when you integrate along here, it gets cancelled by the integral along here, and you'll end up with an answer of 0. You'll get an answer of 0 because, in fact, there would be poles with equal and opposite residues, which would cancel out inside the contour. Anyway, that's the basic strategy. The key thing is firstly recognizing that you need a rectangular contour, and then choosing what w is. But we'll do some examples to see how that works.